The North Pole is an idea we associate with permanence, a fixed point in our conception of the world. The notion that it could wander, let alone swap places entirely with the South Pole, seems fundamentally incorrect. Such an event would render our magnetic compasses unreliable, necessitating a complete revision of our maps. For birds that navigate by this field, the result would likely be profound confusion. And yet, what sounds like a premise from science fiction is a documented geological phenomenon. These geomagnetic reversals are real, they have occurred before, and the process leading to one might be far more dangerous than we typically imagine. What's important to understand is that the potential danger does not lie in the final, reversed state. Instead, the concern is focused on the transitional period. During those times, Earth's magnetic field, the essential shield protecting our planet from deadly solar radiation, could drop to as low as 10% of its current strength. This possibility led one group of scientists in 2021 to predict dramatic climate shifts and even mass extinctions. Others have described scenarios where satellites could be destroyed, electrical grids could go offline, and harmful radiation could rain down on the surface for hundreds or even thousands of years. This is a troubling thought when we consider that Earth is several 100,000 years overdue for its next geomagnetic reversal, and based on fluctuations that scientists are detecting in the magnetic field right now, the build-up to this event may have already begun. This begs a critical question. Should we be worried? What truly happens when the world's polarity begins to shift? To explore this, we can start by understanding where Earth's magnetic field comes from. It is not a given that a planet will have one. The two worlds flanking our own, Mars and Venus, do not. The existence of Earth's field is a fortunate circumstance, as without it, there is a very real chance life would not have been able to arise here in the first place. This protective cocoon deflects harmful solar radiation away from the planet's surface. It allows life to flourish without the constant threat of radiation breaking down DNA, causing mutations and cancers. Scientists are still working to understand all the particulars of why certain planets have fields and others do not. But the current leading theory is that the Earth's core acts as a giant dynamo. A fundamental principle of physics is that electrical fields can be used to create magnetic ones, and vice versa. This is the same principle that allows power plants to operate. Moving a magnet through a coil of wires causes an electrical current to flow, as the changing magnetic field exerts a force on the electrons present there. In a similar way, the motion of electrons creates a magnetic field. This field forms in perpendicular circles around the direction of motion, in accordance with Faraday's law of induction. But the way this applies to the Earth's core is a delicate and complicated process. To begin with, our planet's core needs to be at least partially liquid, a condition which, fortunately, is true. Above the solid inner core that lies at the heart of our planet is a liquid outer core. Here, the pressure is not quite high enough to keep things in a solid state. The temperature in the outer core is incredibly high, reaching 6,000 degrees Celsius at its warmest point. This temperature is so hot that it rivals the surface of the sun. When combined with the lower pressure compared to the inner core, it is more than enough to keep the iron and nickel that makes it up flowing freely. A temperature gradient, dropping as you move away from the center of the Earth, gets this circulation going. Hot, conductive material from the warmer, deeper regions of the outer core rises. It then cools and falls again. This creates loops and currents of flowing material. It is here that our electrical field starts to be generated. But if there are many of these flowing loops, which in theory there would be, why does Earth only have one North Pole and one South Pole? Surely the created magnetic fields would be scattered all over the place. The answer is thought to be an extra force at play that takes all these fields and unifies them, pointing them in the same direction. This force is believed to be the Coriolis effect. Dynamo theory states that the Coriolis effect causes these flows of iron to not rise and fall as straight lines, but as spirals. The spinning of the Earth causes them to be gently spun in turn, creating giant, spring-like columns. As each segment of each spring is creating a magnetic field in a circle around it, the net result is a solid, unified field inside these springs that all moves in the same direction upwards. Meanwhile, the outside of the coil brings that magnetic field looping back down again and back in to the bottom. In short, it creates the well-known magnetic dipole of north and south that we see today. However, if there is anything to take away from this, it is that the process is precarious. It is based on a lot of liquid iron essentially just sloshing around, which is not a very consistent system. Our magnetic field, thus, has little fluctuations and wobbles all the time. We see this in different ways, but a big one is that our North Pole is constantly moving. Since scientists began keeping track of it in 1831, the North Pole has gradually shifted about 1,100 kilometers. Its journey has taken it from an original location in Canada, moving up towards Siberia. Its rate of motion is also increasing, going from 16 kilometers a year to roughly 55 kilometers a year, which is a big jump. This might still be akin to just the momentary wobbles of a spinning top. Yes, it deviates somewhat, but it always remains roughly upright. That is a far cry from a complete reversal. However, scientists are certain that such reversals have happened before. They even have a specific number, 183 times in the last 83 million years. How do they know this? The answer lies locked in the iron of our Earth's surface. When magma erupts from the Earth's mantle, it can contain small amounts of iron. As these particles can move freely in the molten magma, they tend to orient themselves in the direction of the Earth's magnetic field. As the magma cools and hardens into rock, this orientation is frozen in place. Scientists noticed that there were layers of geological history where the iron was pointing one way and layers where it was pointing in the reverse direction. Their explanation was that the entire pole of the planet had flipped. On average, these flips seem to happen every 450,000 years, although the last few have had only 300,000-year gaps between them. Comparatively, it has now been 750,000 years since the last reversal. While it might feel as though we are overdue for a geomagnetic reversal, and some have certainly put forth that idea, the scientific consensus suggests the timing of these events is far from predictable. There seems to be little discernible pattern governing when the planet's magnetic poles decide to trade places. One of the most extended periods of stability occurred during the Cretaceous period, a quiet spell that lasted for 40 million years. The all-time record for magnetic consistency belongs to the Kiemun reverse superchron, which spanned an incredible 50 million years without a single flip, from 312 to 262 million years ago. Researchers are still working to fully comprehend the mechanisms that trigger these reversals. The leading theory, however, proposes that a complex interaction between the Earth's mantle and its liquid outer core can cause a disturbance in the core's rotation. This fluctuation disrupts the elegant, spiraling columns of molten iron, causing them to break down into chaos. In this state, the planet's unified magnetic field dissolves into a sprawling, disorganized tangle that essentially works against itself. During this period of magnetic confusion, several temporary north and south poles might emerge all over the globe. Eventually, conditions settle, and the spiraling flows of iron re-establish themselves, but the final orientation appears to be a matter of chance. This means there is roughly a 50-50 probability that our magnetic North Pole will reappear over the geographic South Pole. This entire process of reassertion can take anywhere from 1,000 to 10,000 years to complete. The question then becomes what this would actually mean for life on the surface. During that transitional phase, before the poles fully re-establish their new positions, Earth's magnetic shield is expected to weaken dramatically, falling to as low as 10% of its current strength. In principle, This reduction could leave our world far more exposed to the constant stream of solar radiation that space directs our way. We might witness auroras illuminating the skies at much lower latitudes than they do today. Rates of skin cancer would likely rise among the human population. Our vital satellites in orbit would find their existing protection insufficient against the onslaught. Harmful radiation could overwhelm their sensitive circuits, leading to malfunctions, complete shutdowns, and possibly even a slow decay from their orbits. The electrical grids that power our modern world would also become significantly more susceptible to solar storms, which could trigger widespread blackouts affecting huge segments of the global population. The loss of electricity and satellite communications would represent a profound blow to our interconnected civilization. The consequences could potentially be even more severe. A team of researchers from the University of New South Wales in Sydney has connected one of the more recent episodes of magnetic field weakening to a major extinction event. This was the Lachamps event, a temporary wobble of the poles lasting about 800 years rather than a full reversal, and it has been linked to the disappearance of megafauna in Australia, including the giant wombat-like diproton and the giant kangaroo known as Procoptodon goliath. These short-lived wobbles are classified as geomagnetic excursions, distinguishing them from complete reversals, and they occur over much shorter timescales. Their transition periods can be as brief as 200 years, compared to the potential 10,000 years for a full flip, making it much more challenging for species to adapt. In a 2021 study, the team argued that a spike in atmospheric radiocarbon caused by the collapse of the magnetic field pointed to significant climate shifts that could have driven these extinctions, and the timing aligns in a rather unsettling way. But just how tangible are these dangers? In truth, the evidence presents a complicated picture. A significant point in our favor is that, aside from this recent study, there is no widespread evidence suggesting that past magnetic reversals have coincided with mass extinction events. It appears that many such flips have occurred throughout Earth's history without leaving any discernible impact on animal or plant life. Even within the context of the Lachamps event study, the extinctions seem to have been geographically confined. The researchers make no claim that this was a worldwide catastrophe. Other regions of the planet were apparently unaffected. It is possible that a perfect storm of factors was at play, where specific local conditions over Australia made its ecosystems uniquely vulnerable to the increased solar radiation. For our global society, it is crucial to remember that these magnetic shifts would unfold over many human lifetimes, even at their most rapid pace. The change would be slow enough for us to recognize and adapt to our new reality. If our current satellites lack adequate shielding, we would have the time to design and launch better protected ones. If solar radiation becomes a greater health hazard, we could adapt our behaviors, such as spending more time indoors, and sun cream formulations could be made more potent to mitigate the increased cancer risks, if not eliminate them entirely. Furthermore, according to NASA, even a significantly weakened field would not leave us completely defenseless. Our atmosphere itself provides a robust secondary shield, capable of absorbing a great deal of radiation. This means we would remain reasonably safe from the worst effects of solar winds and cosmic rays. It would require a period far longer than 10,000 years for our atmosphere's protective ozone layer to be stripped away. Still, it would be surprising if there were not at least some degree of turmoil as we adjusted to living under a diminished magnetic field. Major shifts in the fundamental operating conditions of a society are always challenging, and this is not an entirely abstract concern. It is a fascinating fact that Earth's magnetic field has been steadily weakening for the last 200 years. At its current rate of decline, it would take another 1,300 years to vanish completely, which provides plenty of time for this downward trend to reverse itself. There is no definitive reason to believe this is anything more than a temporary wobble. Adding another layer to this is the South Atlantic anomaly. This is a vast region of the magnetic field, covering most of South America and the adjacent ocean, that is already showing signs of significant weakness. While this zone may not directly affect life on the ground, it is hazardous enough to have damaged satellites and posed a threat to astronauts. The Hubble Space Telescope, for instance, must power down its sensitive instruments each time it passes through this area. Imagine a similar condition extending across the entire globe. That is what we might expect during a pole reversal. What is concerning is that the South Atlantic anomaly has been growing continuously since we began monitoring it. This expansion could suggest the approach of another geomagnetic wobble similar to the Lachamp event, or it might be an early sign that a full-blown reversal is already underway. If a reversal does happen, it is unlikely to be an event that ends civilization as we know it. But if the study on Australian megafauna is any indication, it will not be without its consequences. Some species could face extinction. Humans will be forced to accommodate a very different and more hazardous environment beyond our atmosphere. Learning about geomagnetic reversals and their potential impacts is an intriguing look into the dynamic nature of our planet. While we are not likely to witness one in our own lifetimes, for the generations of humanity that follow us, this topic may prove to be far less hypothetical. They might just be the ones to see it firsthand. If you believe you understand Jupiter, it may be time to reconsider. For decades, scientists debated the nature of the gas giant's core. Was it a solid object, or was it missing entirely? Then, in 2017, NASA's Juno mission rendered that entire debate obsolete almost overnight. The information returned by the Juno probe suggested that both prevailing theories were incorrect, revealing a third possibility that few had anticipated. Jupiter's core, it appeared, was neither a solid sphere nor entirely absent. Instead, the data painted a picture of a diffuse, or fuzzy, central region. This finding presented a significant challenge, as it seemed to contradict fundamental ideas about Jupiter's formation, its internal structure, and even its profoundly strange magnetic field. The mission of the Juno spacecraft was to uncover precisely what lay at the planet's heart, to explore how such a diluted core could have formed, and to understand why this discovery reshapes our thinking not only about Jupiter but about gas giant planets throughout the cosmos. For decades, the scientific conversation concerning Jupiter's core had been dominated by two competing hypotheses. A significant number of scientists favored the gravitational collapse theory, which proposed that Jupiter formed directly from the implosion of a gas cloud under its own immense gravity. This process would have occurred in the colder, outer regions of the early solar system before the planet migrated to its present orbit. In such a scenario, the gas giant would lack a distinct core altogether, existing instead as a continuous mixture of turbulent gases from its surface to its center. This model, however, did not achieve universal acceptance within the scientific community. An alternative view held that Jupiter possessed a solid core composed of heavy elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron. As this solid nucleus grew in size, its gravitational pull began to attract and accumulate vast amounts of hydrogen and helium, which swirled together over millions of years to create the planet we see today. This concept has an intuitive appeal, aligning well with our models of solar system formation. These models suggest that giant planets can be built this way, as ice and rock would condense first in the outer solar nebula, capturing gases through their gravity as they spiraled inward. This theory, known as the core accretion model, predicted a dense, well-defined core with a clear boundary separating the compact center from the gaseous layers above. To settle the question, early missions to Jupiter each attempted to discern what lies beneath the gas giant's dramatic atmosphere. By the 1990 seconds, it was understood that Jupiter was rich in heavy elements, implying the planet was composed of more than just hydrogen and helium. The Galileo mission also provided evidence that Jupiter's magnetic field must be generated somehow by liquid metallic hydrogen in its interior. Yet, if the core is purely liquid, the question of Jupiter's origin becomes more complicated. The standard theory of planetary formation requires a solid nucleus to initiate the process of gas capture. If Jupiter once had such a core but it subsequently vanished, the mechanism for its disappearance was unknown. This raised the possibility that our entire understanding of how gas giants form might be fundamentally flawed. Despite the success of previous missions to Jupiter, the planet's internal structure remained an enigma. The data collected lacked the precision needed to determine whether its core was solid or diffuse, what its composition was, or the exact process by which it generates such a powerful magnetic field. This all began to change with the arrival of Juno. On the 5th of August, 2011, NASA's Juno mission was launched from Cape Canaveral in Florida. Its primary objective was to approach the truth of Jupiter's composition by measuring its gravitational and magnetic fields with unparalleled accuracy. Unlike Galileo, Juno was specifically designed to map the planet's gravitational field in extraordinary detail, achieving a resolution roughly 100 times greater than previous efforts. Upon entering orbit on the 4th of July 2016, the spacecraft commenced a series of highly elliptical polar orbits, swooping down to within just 4,200 kilometers of Jupiter's cloud tops. It repeated this maneuver from multiple angles, a trajectory that made the probe incredibly sensitive to minute variations in Jupiter's gravity. The reason for this intense focus on gravity is its direct connection to the planet's internal makeup. While gravity is often depicted as a perfectly smooth, symmetrical cone, this visualization is a considerable oversimplification. For a planet's gravitational field to be completely uniform, its internal mass distribution would also need to be perfectly uniform. In reality, a closer look reveals a more complex picture. A planet's gravitational field is more like a subtle, intricate landscape. Planets are composed of many different elements and materials, each with its own mass, density, and distribution. These internal differences manifest as tiny, almost imperceptible variations in the planet's external gravitational field. This is why Earth's gravity is slightly different over mountains compared to plains, and it is why scientists were so determined to map Jupiter's gravitational field with such incredible precision. As Jupiter's gravity fluctuates, it causes Juno to accelerate or decelerate slightly. The spacecraft's instrumentation is so sensitive that it can detect changes in its speed as small as 0.01 millimeters per second. Simultaneously, Juno continuously transmits a stable radio signal back to Earth. Scientists can analyze this signal using the Doppler effect. Where gravity is stronger, Juno speeds up, and the radio waves are received at a higher frequency. Conversely, a deceleration due to weaker gravity results in a lower frequency. By repeating these measurements over and over, a very precise map of Jupiter's gravitational field can be constructed, which in turn provides a direct reflection of how mass is arranged inside the planet. While the Galileo mission had managed to sketch Jupiter's gravity in very broad strokes, Juno brought it into unprecedented clarity. What this new, detailed map revealed about Jupiter's core presented a surprising picture to researchers. It turned out that both of the leading theories were incorrect. It seems Jupiter does have a core, but it is not the solid, compact body that had been theorized. Instead, it is a diluted, fuzzy region that gradually blends into the hydrogen-rich layers surrounding it. There appear to be no sharp boundaries. This core is also much larger than anticipated, extending to about half the radius of Jupiter itself. These findings immediately raised a host of new questions, including whether our understanding of Jupiter's formation required a significant revision in light of this exciting new data. A compelling new theory soon emerged to explain this unexpected discovery. It posits that Jupiter may have originally possessed a solid core, but a cataclysmic collision in its early history shattered it, scrambling its material with the lighter surrounding gases to create the diffuse core observed today. The primary issue with this idea is that our standard model for how giant planets like Jupiter form does not work without a solid core to begin with. This leaves two possibilities. Either Jupiter's fuzzy nature developed later in its life, or our formation models are incomplete. In any case, for such a dramatic disruption to have occurred, the impact must have been truly massive, perhaps involving a collision with another young planet. Some scientists speculated that a significant portion of Jupiter's core, perhaps up to half, could be composed of the remnants of this long-lost world. It was a compelling theory that seemed to explain the data, but it encountered a formidable challenge during computational testing. A dedicated team of researchers set out to model this colossal impact using a powerful supercomputer. Their goal was to simulate the precise event that would produce the internal structure Juno had observed. To do this, they designed numerous possible scenarios involving a massive object striking a proto-Jupiter. The team ran multiple simulations, carefully varying the size of the early Jovian planet, as well as the angle and velocity of the collision. Yet, despite their persistent efforts, they could not replicate an event that resulted in the diffuse, fuzzy core Juno had revealed. In every single attempt, the models produced the same outcome. The initial impact would profoundly disturb the planet all the way to its center. But after a period of turmoil, the dense, rocky material from the impactor would invariably settle back down again. This process was much like sediment sinking to the bottom of a quiet pool of water. The material did not dissolve and mix into the rest of the planet as the theory required. Instead, a sharp boundary would reform over time, clearly separating the dense core from the outer layers of hydrogen. This result was a direct contradiction of the Juno data. The collision hypothesis, it seemed, was not the answer, and so it was back to the beginning of the search for an explanation. Curiously enough, the next vital clue in this planetary puzzle did not come from Jupiter itself. It came from its nearest neighbor in the outer solar system. Of course, next door is a relative term when the distance is approximately 648 million kilometers. We have known since 2014 that the subtle waves seen in Saturn's rings are actually caused by vibrations originating deep within the planet. This phenomenon provides us with a unique way to study what the planet's core might be like. It is remarkably similar to how seismology allows us to study the interior of our own Earth. When scientists combined the gravitational field data from the Cassini mission with these precise ring wave measurements, an astonishing new portrait of Saturn's interior was revealed. These combined observations show that at least some portion of Saturn's deep interior does not undergo convection. This was a discovery of profound importance. Inside a giant planet like Saturn, internal heat is constantly trying to escape into space. Under normal circumstances, this happens through the process of convection. It is the same fundamental process that occurs in Earth's mantle, or more simply, when you heat a pot of soup on a stove. Hotter, less dense fluids rise toward the surface, where they cool, become denser, and then sink back down. There, they are heated once more and begin the cycle again. This process repeats over and over in a continuous loop. If Saturn's interior were fully convective, it would thoroughly mix all of its heavier elements throughout its vast interior. There would be no dense, central region to speak of at all. The entire planet would be a completely blended, homogeneous mixture. But if the planet were only partly stable against convection, we would expect to see a gradient of material. In this scenario, heavier elements would be concentrated toward the center, gradually tapering off into the outer layers. And that is exactly what the data from Saturn shows. In 2021, researchers published their findings, arguing that the only way to explain Saturn's ring wave data, its gravitational field, and its partial lack of convection is to conclude that it, too, has a fuzzy core. As it happens, Juno's data also suggests that large regions of Jupiter may not be convective either. Slowly, the dots were beginning to connect. If both Saturn and Jupiter have these diffuse cores, it is more likely that they stem from a common formation process, rather than from a random, catastrophic collision. Scientists are now working to develop a new, emerging theory of how the gas giants came to be. This is a theory in which fuzzy cores are not an anomaly, but a natural and expected part of planetary formation. We have not yet arrived at a complete and tidy explanation. But it has become abundantly clear that the old assumptions we held about the largest planets in our solar system are incorrect. Jupiter and Saturn are not simply made up of a solid core and a gas envelope, nor do they have completely mixed interiors. Their fuzzy cores are composed of a compositional gradient. This means more heavy elements are concentrated in the center, and these elements dissolve outward into the gas envelope without any clear boundary. This complexity and uneven mixing challenges our current models for planetary evolution. Where our old, simplistic models predicted that the giants would cool in a predictable way over time, these new models with fuzzy cores do not follow the same patterns. The same is true for all the gas giant exoplanets we have discovered and studied so far. In the meantime, there is one other piece of the jigsaw that needs to fit the puzzle created by Jupiter's fuzzy core. That piece is its strange and powerful magnetic field. For years, scientists have known that Jupiter's magnetic field is generated through a dynamo process in its metallic hydrogen layer. This layer spans a region from 20,000 to 60,000 kilometers deep. Here, temperatures can exceed 30,000 Kelvin, and pressures are millions of times greater than on Earth's surface. Under these extreme conditions, hydrogen exists in a liquid state. But even more incredibly, its electrons become delocalized, meaning they are free-flowing. This creates an electrically conductive metallic state of matter. Coupled with Jupiter's very fast rotation, this liquid metallic hydrogen creates a dynamo effect. The exact process of how this dynamo is powered, however, remains a mystery. Whatever it is doing, it is working exceptionally well. Jupiter has the largest, strongest magnetic field of any planet in the whole solar system. Its magnetosphere spreads 7 to 21 times the diameter of Jupiter, tapering into a tadpole shape behind it that extends all the way to Saturn's orbit, about 1 billion kilometers away. However, Jupiter's magnetic field also has some quirky characteristics. It is much stronger in the northern hemisphere than in the southern hemisphere. It has intense, localized magnetic spots, and it has 2 magnetic south poles. Scientists hoped Jupiter's fuzzy core might actually explain some of these strange behaviors. Frustratingly for them, the opposite turned out to be true. Jupiter's fuzzy core actually complicates, rather than explains, its magnetic field. Magnetic fields in planets are usually created by swirling motions of electrically conducting material, like the metallic liquid hydrogen in Jupiter. However, Juno data showed that large regions of Jupiter, much like Saturn, seem to be at least partially non-convective. Researchers modeled the fluid dynamics of Jupiter's interior in 2 potentially non-convective regions to see how they would affect the magnetic field. One region was in the upper part of the planet's interior, and the other was lower down, corresponding to the dilute core. They concluded that the upper stable layer helps explain Jupiter's magnetic field even better than previous solid core models did. However, the lower region representing the non-convective dilute core did not explain Jupiter's magnetic field on its own. In other words, a completely stable, fuzzy core produces a magnetic field that is very different from the one we actually observe. Now, researchers believe Jupiter's dynamo is more complicated than originally thought. It is possible that below the uppermost molecular hydrogen layer, Jupiter has a layer of helium. This helium may rain down through the liquid hydrogen, much like oil passing through water. Some think this process could have an effect on the magnetic field. An alternative theory proposes that Jupiter's dynamo does not function in a uniform manner as Earth's does. Instead, this view suggests the planet's asymmetrical magnetosphere arises from variations in density, electrical conductivity, or perhaps both. Ultimately, however, no one is certain precisely how this immense magnetic field is generated or what contribution the fuzzy core makes to its existence. There is one thing we understand with absolute clarity. Jupiter's magnetic field is the engine behind the largest and most brilliant auroras in our solar system. On our own world, these light shows are confined to a window of 4 to 6 months. Yet on Jupiter, they are a permanent feature, blanketing the poles in a continuous, dazzling exhibition of color that is hundreds of times more powerful and energetic than the displays we are familiar with. By assembling a sequence of far ultraviolet images from Hubble's imaging spectrograph, scientists have been able to produce videos that show these auroras in motion. The spectacle is truly magnificent. Despite the discoveries made by the Juno mission, Jupiter continues to hold its secrets tightly. We still lack an understanding of how its diffuse core came to be, and we do not know how permanent this feature is. Is the fuzzy core a stable structure destined to last for billions of years, or is it gradually dissolving into the gaseous layers that surround it? The nature of its relationship to the metallic hydrogen above it and to the magnetic field that Juno so carefully mapped remains a puzzle. It is also unclear if this entire arrangement is simply a natural stage in the formation of a gas giant. For now, we cannot say with certainty, but it is clear that our current models do not capture the complete picture. With continued study, there is hope that we can slowly find answers to these questions, one by one. And yet, the more we learn, the more new questions seem to emerge. This relentless pursuit of understanding is a defining characteristic of our humanity. Imagine for a moment standing on a quiet hill, observing the sky erupt in a symphony of color as the sun crests the horizon. It is a daily event that many of us may overlook. The warm tones of orange, red, and pink paint the atmosphere. This beautiful sunrise, however, represents only the final stage of an incredibly long journey for the light that reaches us. If we were to trace the path of these photons backward, from their destination in the retina, at the back of the eye, through Earth's atmosphere, across the 150 million kilometer expanse that separates our world from its star, and finally down through that star's varied and turbulent layers, we would find the source of the warmth on our skin and the colors in the sky. We would arrive at the sun's core, a nuclear furnace that has been burning for 4.5 billion years. Born within a cosmic nursery from the material of long-dead stars, the glowing sphere of searing plasma that anchors our sky is the result of intricate forces that have unfolded over eons. Our journey, then, will take us back in time, tracing the sun's origins, exploring its complex layers, and mapping the very elements that constitute its structure. We will venture deep into the heart of our star to learn what secrets might lie behind its blinding veil of light and time. To comprehend how the sun was formed, we must travel back to a time before our solar system existed, approximately 4.6 billion years ago. In a relatively tranquil corner of the Milky Way galaxy, a vast cloud of gas and dust, known as a giant molecular cloud, drifted through the silence of space. This was no ordinary cloud. It was enormous, potentially stretching for hundreds of light years and containing a mass equal to millions of suns. Within this cosmic nebula were the scattered remnants of ancient stars which had long ago depleted their nuclear fuel and exploded as supernovae, seeding the cosmos with their enriched materials. This stellar debris was composed of a mixture of elements, including the primary building blocks of stars, hydrogen and helium, as well as heavier elements such as carbon, oxygen, nitrogen, and iron. The existence of these heavier elements made this particular molecular cloud a fertile environment for the formation of new stars and their planetary systems. A cloud of this magnitude, however, requires an external event to initiate the cascade of collapse that leads to stellar birth. Scientists theorized that this trigger could have been a shockwave from a nearby supernova explosion. Such an event would have compressed sections of the cloud, causing it to fragment and collapse into regions of greater density. This collapse was the very beginning of the pre-solar nebula, the dense pocket within the molecular cloud from which our solar system would eventually emerge. Some researchers have even put forward a name for this hypothetical exploding star, Coatlicue. Named for the Aztec goddess of the earth and fertility, Coatlicue serves as a symbol for the cycle of death and rebirth, where the end of one star provided the seeds for the formation of new ones. As the gravitational collapse of the giant molecular cloud proceeded, it did not form a single, massive object. Instead, it broke apart into numerous dense clumps. This fragmentation is the result of a phenomenon called Jeans instability, which takes its name from the British physicist Sir James Jeans. The Jeans length describes a critical scale within a cloud, where the inward pull of gravity is perfectly balanced by the outward push of the cloud's internal gas pressure. When any given section of the cloud grows larger than its Jeans length, it will inevitably collapse under its own weight. Because of variations in density and temperature, different regions inside the molecular cloud surpassed this critical length at different times. As these areas became gravitationally unstable, they collapsed independently, leading to the formation of multiple protostellar cores rather than a single massive body. This protostellar core represented the earliest phase of our Sun's life that was recognizably star-like. It was a sphere, being crushed into an ever-tighter ball by the unyielding grip of its own gravity. The core was enveloped by infalling gas and dust. As more and more material was drawn in, the core grew denser and hotter, preparing the way for the next stage of stellar development, the protostar. Once a protostellar core became sufficiently dense and hot, it transitioned into a protostar. At this point, its central region had warmed to the degree that it started to radiate light and heat, energy released purely by its gravitational contraction. Its core, however, had not yet reached the extreme temperatures needed to ignite nuclear fusion. As the protostar continued to gather material and increase in mass, the pressure and temperature at its center rose dramatically. Our Sun remained in this embryonic state of contraction and heating for millions of years. It eventually built up its core temperature to roughly 10 million degrees Celsius, the point at which hydrogen nuclei finally began to fuse into helium. In that instant, the Sun was born. At this stage, the inherent spin of the material enveloping the infant star is what induces its rotation. A cloud of this immense scale will always possess some slight turn, as absolute stillness is an impossibility in the cosmos. The principle of conservation of angular momentum then dictates that as the cloud collapses into a more concentrated space, its spin must accelerate dramatically, a process analogous to an ice skater pulling their arms inward to spin faster. Along the rotational equator, some of this material gains enough velocity to settle into orbit. Above and below this plane, however, the momentum is too weak to overcome the protostar's powerful gravitational influence, and that matter spirals inward. This dynamic ultimately causes the cloud to flatten into a structure known as a protoplanetary disk. This disk becomes a kind of cosmic lottery. As its contents cool and aggregate, a relentless process of formation and destruction will give rise to planets, moons, asteroids, and comets. Some material will lose its momentum and be drawn into the star, while other adjacent matter is destined to become the various bodies that constitute our solar system today. With its newfound capacity to fuse hydrogen atoms into helium, the Sun could finally generate the energy required to push back against the gravitational forces attempting to compress it further. The energy flowing from these fusion reactions produced an outward radiation pressure that precisely counterbalanced the inward gravitational pull of the gas, allowing the young star to achieve a stable condition known as hydrostatic equilibrium. In this state, the star no longer contracts under its own weight. and it enters a long, stable phase of its life called the main sequence. This delicate interplay between outward internal pressure and inward gravitational crush is the central tension that defines every stage of life for the Sun and all other stars. We saw this dynamic during the initial collapse. We observe it now as the star settles into its main sequence phase, and it is the same force that will eventually lead to its dramatic end. For now, it is worth examining the process of nuclear fusion itself, and how it is able to keep an object as massive as the Sun stable for billions of years. To comprehend how nuclear fusion operates in the Sun, we must look at the extreme environment within its core. Today, temperatures there reach approximately 15 million degrees Celsius, while pressures are more than 250 billion times that of Earth's atmosphere. Inside this searing cauldron, hydrogen atoms are stripped of their electrons, creating a plasma composed of free protons and electrons. Under such intense conditions, these protons, which are normally repelled by their shared positive electric charges, are forced into extremely close proximity. The force that typically holds them apart is the Coulomb force, an electrostatic repulsion between positively charged particles. It is the very same resistance you feel when trying to push the like poles of two-bar magnets together. Overcoming this force represents the primary challenge for nuclear fusion to take place. Despite the tremendous kinetic energy of the protons in the Sun's core, most of their collisions are still not energetic enough to breach this Coulomb barrier. Under conventional physical models, protons require immense energy to get close enough for the strong nuclear force to bind them. This barrier is so significant that in the early 1920 seconds, physicists, using a classical understanding of particle interactions, concluded that fusion should not be possible at the temperatures and pressures found within the Sunday. The solution to this puzzle would require a scientific model that has come to explain many of the universe's seemingly impossible phenomena: quantum mechanics. The quantum revolution of the 1920 seconds introduced the concept that particles can behave as both particles and waves. One of the intriguing results of this is quantum tunneling, where a particle has a certain probability of passing through an energy barrier even when it lacks the classical energy to go over it. In the Sun's core, quantum tunneling allows a small fraction of protons to effectively bypass the Coulomb barrier without needing to climb it. So, even though these protons do not possess enough kinetic energy to directly overcome the electrostatic repulsion in a classical sense, quantum mechanics affords them a chance to simply appear on the other side of the barrier. To visualize this, one can imagine a diagram of the Coulomb barrier as a high-energy hill, representing the repulsive force between two protons at various distances. The energy needed to climb over this hill is represented by its peak. Classical calculations would require the Sun's core to be thousands upon thousands of times hotter, reaching into the billions of degrees Celsius for protons to clear this peak. But quantum mechanics permits the probability wave of a proton to tunnel through this barrier, materializing on the other side without ever going over the top. This tunneling effect is what enables fusion to occur in stars like our Sun, despite the seemingly insurmountable Coulomb barrier. Once a proton has tunneled through, it gets close enough to another proton for the strong nuclear force to take over. This force, which is far more powerful than the Coulomb force, operates only at very short ranges on the order of femtometers, where 1 femtometer is equal to 10 to the power of -15 meters, roughly the size of a single proton. The strong nuclear force then binds the protons together. This, however, is only the first step in a series of nuclear events known as the proton-proton chain. This chain reaction is the dominant fusion pathway in the Sun and other stars of similar size, accounting for roughly 99% of the Sun's energy production. It begins when two free-roaming protons combine to form deuterium, a heavy isotope of hydrogen, along with the emission of a positron and a neutrino. This particular step is rare but essential, as it allows the fusion process to continue. The deuterium then rapidly fuses with another proton to form helium-3, releasing a high-energy photon, a gamma ray. In the final step, two helium-3 nuclei collide and fuse to form helium-4, releasing two protons and a significant amount of energy in the form of radiation. While the proton-proton chain is the dominant fusion process in the Sun, there is another pathway at play, particularly in stars that are hotter and more massive than our own. This pathway is known as the CNO cycle, which is short for carbon, nitrogen, and oxygen. In this cycle, the nuclei of carbon, nitrogen, and oxygen act as catalysts to fuse protons into helium. The CNO cycle is a process that operates with greater efficiency at much higher temperatures, which is why it contributes only a small fraction of our own Sun's energy production. The immense power generated within these fusion reactions stems from a tiny amount of mass being converted into energy, a fundamental principle articulated by Einstein's famous equation, E equals mc squared. During the fusion process, the mass of the final helium-4 nucleus is infinitesimally smaller than the combined mass of the four protons that formed it. This missing mass is not actually lost, but is instead transformed into the radiant energy that flows outward from the Sun. Every single second, the Sun converts about 4.3 million tons of its mass directly into energy. What this means is that the Sun is perpetually losing mass. To place this staggering figure into context, it is the mass equivalent of approximately 3 million cars being turned into pure energy with each passing second. This is the very energy that powers our star, ultimately providing the light and heat that sustains life on Earth. However, before the photons created in these reactions can reach our world and the rest of the solar system, they must first navigate the 700,000 kilometers of the chaotic solar interior that lies above them. To truly appreciate the Sun's complexity and its stratified structure, we can follow the path of a single photon, a particle of light, from the moment of its birth in a proton-proton reaction all the way to the surface. This odyssey is anything but direct. In fact, it is a journey that will likely take thousands, or perhaps even hundreds of thousands, of years to complete, as the photon must pass through several distinct solar layers, each defined by its own unique properties and behaviors. As we know, our photon's journey begins deep within the core, a region extending to about 25% of the Sun's radius, yet containing nearly half of its entire mass. The core is also a place of incredible density, measuring around 160 grams per cubic centimeter, which is more than 20 times denser than solid iron. As a point of reference, if your phone were crafted from material this dense, it would feel as heavy as a large sledgehammer. For our newly formed photon, this extreme environment means it is so tightly packed with other particles that it cannot travel far before being absorbed by one of its neighbors. Of course, a moment later, that particle will re-emit the photon, sending it off in a completely random direction into the dense plasma of the core, where another particle will catch and release it once more. The experience is somewhat like trying to move through an incredibly dense crowd, where every few steps result in a collision that forces a change in direction. This constant cycle of absorption and re-emission is what lends the core its chaotic character, turning the photon's journey into what is best described as a random walk rather than a straight path outward. This erratic movement of photons is reminiscent of Brownian motion, where particles suspended in a fluid appear to move randomly due to collisions with smaller, fast-moving molecules. There is absolutely no preference for the direction in which a photon might be re-emitted from a particle that has just absorbed it. It is theoretically possible for a photon to travel nearly all the way to the Sun's surface, only for random chance to send it ricocheting back toward the core. Adding another layer of complexity, as these photons are continuously absorbed and re-emitted, their energy gradually diminishes, transforming from powerful gamma rays into X-rays, and eventually into visible light as they slowly make their way toward the Sun's outer regions. Understanding the processes at work within the solar core has presented a formidable challenge for astronomers. The core itself is completely hidden by the sun's outer layers, meaning we cannot observe it directly with any form of light. Instead, scientists have devised ingenious methods to infer the dynamics of the roaring furnace deep below. One of the most crucial techniques is helioseismology, which involves studying the waves that ripple across the sun's surface. In much the same way that seismologists on Earth study earthquakes to understand our planet's interior, helioseismologists measure the surface vibrations caused by sound waves traveling through the sun. These sound waves are subtly altered by the temperature, density, and composition of the layers they pass through, allowing scientists to build detailed models of what is happening in the depths. Solar neutrinos, those elusive subatomic particles released during the fusion reactions in the core, offer another window into this hidden realm. Neutrinos interact so weakly with matter that they are able to travel directly out of the sun in just 2 seconds, almost entirely unaffected by the dense plasma that ensnares their photon counterparts. For many decades, neutrino detectors on Earth consistently measured fewer of these particles than theoretical models predicted, a puzzle that came to be known as the solar neutrino problem. The mystery was finally solved when scientists discovered that neutrinos can change their properties, or flavors, during their journey to Earth, a finding that confirmed both our understanding of particle physics and the nuclear processes occurring in the sun's core. After its immense journey, the photon eventually enters the radiative zone, which extends from the edge of the core out to about 70% of the sun's radius. Within this layer, temperatures gradually decrease from 15 million degrees to around 2 million degrees Celsius. The density of matter also drops significantly, from a density comparable to gold in the zone's lower depths to less than that of water near its upper boundary. The dominant method of energy transport here is still this frenetic process of photons scattering through the plasma, carrying their energy slowly, on average, toward the surface. As the density of the plasma continues to decrease with outward distance, our photon finds slightly more room to move, capable of making larger leaps between its interactions with other particles. Yet even here, far outside the core, the sun's material remains so opaque that a few centimeters of it could block as much light as hundreds of meters of water. We are able to construct such precise models of the sun's interior thanks to frameworks like the Standard Solar Model, or SSM. This is a mathematical structure built upon fundamental principles of physics, including hydrostatic equilibrium, energy conservation, and radiative transfer. It essentially uses our understanding of how materials and fluids behave in laboratories on Earth to infer the properties of a place far beyond our physical reach. The complex equations of the SSM model how energy is passed between particles, describing the way photons are transported through the dense solar plasma. This allows us to calculate how transparent the solar material is to radiation at various temperatures and densities. From that information, we can then determine precisely where the radiative zone ends and the next layer of the sun begins. This is one of the most remarkable aspects of mathematics. It provides a way for us to explore environments that we can never hope to visit in person. The mechanism is analogous to quantum tunneling, which allows protons to overcome the Coulomb barrier and generate the very photons we are now observing. As our photon travels toward the upper limit of the radiative zone, it enters the tachocline, a thin boundary layer that separates the radiative zone from the convective zone above it. This area is an environment of stark juxtaposition, where the relative calm of the radiative interior meets the turbulent, churning motion of the convective region. The unusual physics at play within this remarkably slender boundary are believed to be instrumental in the solar dynamo, the process that produces the sun's magnetic field. The tachocline is thought to be the place where the magnetic field is twisted and amplified, ultimately giving rise to the sunspots and solar flares that characterize the star's surface. After passing swiftly through this narrow band, Our photon enters the convective zone,